Alright, so let's look at this problem. Um, okay, so we're looking at bilinear functions, and those are functions that satisfy these three equations. Um, and so why are they called bilinear? Well, if you sort of ignore the second coordinate and focus just on the first coordinate, then these two equations say that you can pull scalars outside and you can break up addition. And that's pretty much exactly what linearity is with respect to the first coordinate. And if you look at these two equations that I'm putting in boxes, well, if you ignore the first coordinate, then this says that you can bring out scalars and bring out addition with respect to the second coordinate, which is the same as being linear in the second coordinate. So these are functions which are linear in both the first coordinate and the second coordinate. So it's kind of like linear in two ways, so like bilinear. That's why we call them that. So anyways, part A is to prove this equation, and this is actually a little tricky. I guess it really isn't, but you definitely have to think a little bit. Like there's a couple things to prove here. So, given h, two vectors h and k which are not equal to 0, write h as the norm of h times h hat, and k equals the norm of k times k hat, where the norm of both h hat and k hat are 1. And the reason that we're able to do this is we're assuming that h and k are non-zero, so basically h hat tells us, like if you look at the vector h hat will tell us what direction. It's a unit vector that's pointing in the direction of h, and then the norm of h tells you how far to go in that direction. This is kind of like how you can write you can write all complex numbers in the form r times e to the power of I theta, where r is the radius and theta is the angle. So theta tells you which direction to point in, and r tells you how far to go in that direction. Similarly here, h is equal to the norm of h times h hat, where h hat tells you what direction you're pointing in, and the norm of h tells you how far to go in that direction. Okay, so we have this. Let's see here. Note that if we let capital M be, now this is going to be the max of f of ei comma ej, where I is between 1 and n, and j is between 1 and m. It's finite, then. Okay, so what have I done here? So basically what we're doing here is that f has two inputs, the first coordinate and the second coordinate. In the first coordinate, you're inputting the argument is a vector in Rn, and the second argument is a vector in Rm, which Rn and Rm both have bases given by these standard basis elements, Ei and Ej, where I and j vary over the corresponding indices. So why am I doing this? So what we can do, and also there are finitely many indices here, so this set of things of the form norm of f of ei comma ej, where I and j vary in these different regions, how many elements are there in here? There are n times m elements, because those are the ranges of I and j. And so if you've got finitely many positive numbers, then the largest one must be a finite number, obviously. Okay. So now if we write h hat as the sum from I equals 1 to n of ai times ei, and k hat is the sum from j equals 1 to m of bj times ej. Then, now why can we do this? This is just because this is what it means to be a basis element. The fact that e1 through en is the basis of Rn means that any vector in Rn can be written of the form the sum of ai ei, where the i's range from 1 to n, and each ai is a real number and each bj is a real number. Okay, so then, since h and k being unit vectors implies ai is less than or equal to 1 and bj is less than or equal to 1 for all I and j, we have... Okay, so there's sort of a lot of things here. It all sort of makes sense, but I suppose I could have written them in a more organized fashion. But basically what we need here is we need this m. These are the ingredients of this proof. We need this capital M here. And we need to write h hat and k hat as a sum of basis elements. And we need to keep in mind that each of these coefficients here must be less than or equal to 1, because if any coefficient was greater than or equal to 1, then the corresponding vector would have norm at least as big as the scalar in that particular component, which would be greater than 1, which would contradict the fact that these are unit vectors, and thus have norm exactly equal to 1. So anyways, once we have all of this, so this is what we have been looking for. This is what we're trying to do. We have f of h comma k. So this is equal to the norm of f of... Now we can take the sum from I equals 1 to n of ai ei, because that's the same as h hat, and we can take the sum from j equals 1 to m of bj ej, because that's the same thing as k hat. Okay, and now what I'm going to do is, and this is something that you might have to write out this sum for really small numbers n and m in order to convince yourself of this, but the fact that for bilinear forms you can take out addition from within an argument to outside the function, you can bring these sums outside of the function. So this actually becomes the sum from I equals 1 to n, sum from j equals 1 to m of f of ai ei and bj ej. Okay, and the fact that you're able to do that again, you might have to write out a few examples just to convince yourself of this. But if you're really comfortable with this, then you can just go ahead with this. And so now what can we do here? Well, remember, f is bilinear, so not only can we pull out the sums, which we just did, but you can also pull out the ai's and the bj's. So this is actually equal to, here, I'll write it here. This is equal to sum from I equals 1 to n, sum from j equals 1 to m, and we can pull out the ai's from the first coordinate, and we can also pull out the bj's from the second coordinate, or argument, whatever. And then we're just left with f of ei comma ej. And now, remember that when you're taking absolute values here, you can bring, an absolute value of a sum is going to be less than or equal to the sum of the absolute values. And so, therefore, this is less than or equal to, here, I'll write it on the next line just in case. This is less than or equal to the sum from I equals 1 to n, the sum from j equals 1 to m, and now we just have the absolute value of the stuff on the inside. And so I'm going to write this as ai times bj times f of ei comma ej. And then recall that the product of, or the absolute value of a product is the same as the product of the absolute values. So this is equal to this sum again. And now we have ai times bj times the norm of fei comma ej. Okay. And so now what we have is, remember, so since norm of h hat and norm of k hat equals 1, this means that the absolute value of ai is less than or equal to 1, and the absolute value of bj is less than or equal to 1. So that was my mistake. But yeah, the absolute values there are very important because we need to use that here. So now we're going to write this as less than or equal to, and we can replace ai and bj with 1 because we're just increasing things. So now this is just the sum from I equals 1 to n, and the sum from j equals 1 to m. So we've replaced ai with 1, we've replaced bj with 1, and now f of ei, ej. Now each of those is going to be less than or equal to capital M, because m was selected to be the largest possible example of that. So we can just replace f of ei comma ej with capital M. And so this is the sum from I equals 1 to n, sum from j equals 1 to m of capital M, and this is equal to n times m times capital M. And note that we don't have h hat or k hat occurring in this form here, meaning that we found a uniform bound for f of h hat comma k hat. No matter what h hat or k hat you choose, of course h hat and k hat have to be unit vectors, but regardless of which one you choose, you have an upper bound for the norm of f of h hat and k hat. And this is really important because we need this fact to prove part A. Perhaps you could have you might have been able to do something else, like, for example, functions like this, like, I don't know, there might be some sort of continuity type argument that you can use, or maybe you can apply like the theorem that tells you that linear functions are bounded, but then you'd have to play with, like, you have linearity like in the first coordinate if you fix the second coordinate, so there could be some things that you have to mess with there. This is just the first thing that I thought of that worked. There might be a slicker way to find a uniform bound for the norm of f of h hat comma k hat, where h hat and k hat are unit vectors. So if you can, that's what we need here. We need a uniform bound. There might be an easier way to do it, but this way works. That's what I'm trying to say. Okay, so now we can actually prove part A. Since the norm of h comma k for any two h and k is always going to be greater than the norm of h, and this is a fact that we've used in other exercises. This is a really useful tool, especially for analysis exercises where you need to prove inequalities. So anyways, now let's move on to the actual inequality that we're trying to prove here. So we're looking at the limit as h comma k goes to 0, the 0 vector that is, of 0. So we have the norm of f of h comma k on top, and on the bottom we've got h comma k. Okay, so now this is going to be equal to the limit, and I'm not going to write h comma k going to 0 every single time because I don't feel like it. So anyway, so h is, again, this is the same as the norm of h times h hat, the norm of k times k hat. And we're again dividing by h comma k. So now what I'm going to do is, well, then we can pull out the norm of h and pull out the norm of k. And so this is just the limit of, and how I'm going to write this is going to be norm of h times norm of k, and we're going to divide by h comma k here. And then what we're left with on top is the f of h hat comma k hat. And so now we're going to write this as less than or equal to. So in the denominator here, we've got the norm of h comma k. If you replace the norm of h comma k with h in the numerator, then you have a greater than or equal to. But if you're making this replacement in the denominator, then the inequality flips. And so this is less than or equal to the limit of norm of h times norm of k over, and then we'll replace it with the norm of h. You could have replaced the denominator with the norm of k as well. It doesn't matter. So we've got this part, and then the norm of f of h hat and k hat. Well, we have a uniform bound for that, so this inequality also holds if we replace that that part of the term with n times m times capital M. And so now this is going to be, we can n times m times capital M, this is just some finite positive number, we can bring that out front, and we multiply by the limit of, well, the h's cancel, and so we just have the norm of k. So as the vector h comma k goes to 0, then obviously the vector k has to go to 0, which means that the norm of k has to go to 0, and so this is equal to 0. And that's what we wanted to arrive at. So note that we had to sort of do two things here. We had to, well, first we had to take this fraction, we had to break it up into, like, you had the scalars that came out, and then you had the f applied to h hat and k hat, where h hat and k hat are unit vectors. And then in order to proceed from there, we need to do some cancellation in the first part involving the h's and the k's, do some cancellation to make that something that would go to 0, and then also, for the second part, find a uniform bound, which we could then, which would not blow up as we take h and k to 0. Okay, so now, what have we proven? We've proven that the limit is less than or equal to 0. So, technically, we need to include this final remark. Clearly, the limit as f of kh over hk is greater than or equal to 0, and that's obviously true because for every choice of h and k, you'll get something positive, and so in the limit, you have to end up with something positive. And hence, finally, we get the desired conclusion of the limit of f of h comma k over hk equals 0. Okay, and that's what we wanted. Alright, so that does that, and now we want to move on to part B. Okay, let's do part B of this problem. Like I've written, we want to prove that dfabxy equals f of ay plus f of xb. So what do we have to prove? We have to prove that limit formula that you have for derivatives applies here. But the other thing that we need to know is we need to know that this is in fact a linear function, or a linear transformation, because the derivative is a function, and it has to be a linear function. And when I was first doing this exercise, I was like, wow, well, I mean, obviously this is linear, but I guess it's not that obvious. So I want to take some time to actually confirm that this is in fact linear. So dfab, again, this is given any a comma b, the derivative is we have the derivative at that point is its own function. And it is linear because for every single choice of, if you give me any 2 points x comma y and z comma w, elements in Rn cross Rm, remember this is the domain of f, and so it's also going to be the domain of the derivative of f. So for every single this, and for every single constant lambda in R, we have now one way to prove linearity, like probably the most concise way, is you take a linear combination inside the argument, and you prove that you can bring this linear transformation outside. The ability to prove, you can prove that this is logically equivalent to proving that something's linear, because the fact that you have to deal with both this addition sign and this scalar, being able to deal with both of those gives you the two conditions that you need for linearity. So anyways, if we want to add these two vectors of Rn cross Rm together, then we combine them like so. This is just the first argument is going to be x plus lambda z, and the second argument is going to be y plus lambda w. So again, z is a vector in Rn and w is a vector in Rm. So now what do we do with this? Well, now we just apply the formula. We know that's f of a comma y plus lambda w plus f of x plus lambda z comma b. And now we use the fact that f is bilinear to prove that, well, if you take this first part, you can break it up into f of a comma y plus f of a comma lambda w. But also because it's bilinear, you can bring that lambda out front. So the first term is equal to f of a comma y plus lambda times f of a comma w. And then to this, you can add f of x comma b plus, and then again you can bring out the lambda, and you get lambda f of x comma z. And now you can group the terms without y's together. And you can group the terms with, or the terms without the lambdas together, and then you group the terms with the lambdas together. Of x, z. And now we can see that these first two terms, if you combine them, well, that just by definition is the derivative evaluated at x comma y. And then you add lambda, and then the thing in the parenthesis here, these two terms, these can combine to give you the derivative at ab, this derivative function evaluated at z comma w. And that's exactly what we wanted to do. We brought the addition and the scalar multiplication outside. And so therefore we have a linear function. As for the limit part of the definition of a derivative, what we have to do is we have to prove that the limit as h and k goes to the zero vector of, and now we have this huge fraction thing, the denominator is going to be h comma k, and the numerator is going to be f of a plus h, b plus k. Here we're replacing x with h and we're replacing y with k. So now we take f at a, b, we increase both coordinates by a little bit, then we subtract f at a, b, and then we have to subtract the derivative function. So we subtract the formula that we claim to be the derivative. And so that, of course, is f of ay plus f of xb. So if we're subtracting that, then we subtract f of a comma y, and we subtract f of x comma b. No. But remember, I'm replacing x with h, and I'm replacing y with k. So this is what it should look like. Okay, so now we're good. Okay, so now we take this, and this is the limit of, again, we have 1 over the norm of h comma k. And now, because f is bilinear, we can break up this f of a plus h comma b plus k. This is going to become f of a, b, plus f of a, k, plus f of h, b, plus f of h, k. And now perhaps you can sort of start to see what's going to happen here. F of ak minus f of h, b. So what's going to happen? We have this positive f of ab here, and we have this negative f of ab here. We've got positive ak here, negative there, positive fhb here, negative fhb there. And so what we end up with is the limit. The only thing that's left here is the norm of f of h comma k. And in the denominator, we still have this thing. But this is exactly what we wanted to prove in part A is 0. And this completes part B. So now, if you were to actually go about this, if you were not given the formula for the derivative and you wanted to find it out, basically what you would do is you would just look at the difference between these two things, and you would note that you could break up the first part into something involving AB and 3 other terms not involving AB. So you'd have to figure out, of the remaining things, what stuff will go to 0 as the denominator goes to 0, and what stuff would be things that you would want to include in the actual derivative itself. Or if you weren't to do it that way, there's probably some more elegant way of seeing that the derivative should be this. But I just sort of went through this and just took the formula that they gave me, and I was like, well, we have a definition for what it means to be a derivative, so let's confirm that the definition holds. Okay, so lastly, we want to do part C. So to prove theorem 2-3 part 5 is a special case of part B. We're going to let p of xy be the function given by x times y. So if p happens to be a bilinear function, then part B applies to it. So let's prove that this function p is in fact a bilinear function. So we have p of ax comma y. Well, this is just ax times y. But that's a times xy, so that's a times the product of x and y, so that's a times xy. And likewise, we have p of x ay equals xay, and we can bring the a out front, and so this is again this. Okay, so we have, you can bring scalars out of both arguments. As for addition, bringing it out of the first argument, p of x1 plus x2y equals, well, this is just x1 plus x2 times y, and you just factor that out, x1y plus x2y. So the first part is the product of x1 and y, and the second one is the product of x2 and y. By the way, if you haven't picked up on it, so the reason that they use p for this function is because p stands for product. And so that's why we're using p as the function name here. Anyways, so lastly, if we want linearity in the second coordinate, well, it's going to be the exact same thing. I suppose, like, this part of the proof is simple enough that the details aren't really super important. Like, it's useful to go over, like, for yourself if you don't immediately see it, but I suppose it's not super necessary to write out these details, because all of these steps are pretty elementary. Hence, p is in fact bilinear. Thus, by part B, we have the derivative of p at AB. The derivative of p at the point AB is a function of x and y, which gives you p of ay plus p of xb. But this is ay plus bx, just by the definition of p, and this is, of course, the same as bx plus ay, which is the conclusion of 2-3 part 5. Remember, it said that if p is the function given by this, then p is differentiable, and its derivative is given by the derivative of p at ab is a function of xy, which evaluates to bx plus ay. And so, of course, there was a different proof for that, but this shows us that we have a different way of obtaining this formula as a special case of the derivative formula for bilinear forms. And yeah, so, well, not bilinear forms, bilinear functions. These are basically bilinear forms, sort of, yeah. You'll learn about that in like abstract algebra if you haven't learned about that. But those are important, and it's basically a similar idea. It's sort of like a type of inner product in which you have linearity in both coordinates, and there's a lot of stuff you can do with them, and they're really important. And the fact that they're really important is seen by the fact that it comes up here, and we're able to prove things about them, and in fact, we're able to generalize previous theorems from this book. But anyways, we've finished everything that we needed to prove about this exercise, and so we are done.